Hi everyone, in this video I am going to discuss how to graph a rational function. So let us have a review. What do you mean by domain? Domain is the set of all permissible values for x, because there are some instances that a value or a number is not part of or cannot be the value for x. Same goes with the range. Range is the set of all values for y. And there are some instances also that there are values that is not included in the range. Okay? So we define these two, domain and the range, in our discussion here at rational function. Okay? For letter C, or for the third one, let us have the zeros of a function. How are we going to determine the zeros of a function? It is just the x-intercept. Meaning to say, we replace y by 0 and then solve for x. Okay, we replace y by 0 and then solve for x. And for our y-intercept, we replace x by 0 and then solve for y. Okay, x-intercept is the point on the x-axis where the graph intersect the x-axis. Okay? And the y-intercept is the point at y-axis where the graph intersect the y-axis. Okay? So I'm not going to discuss the domain range x-intercept of y-intercept of y equals to x plus 1. It is for you to practice. So for our objectives in this video is for you to determine the intercepts, zeros, and asymptotes of rational function. And moreover, you must be able to graph the rational function. Okay, before we proceed to our examples, you must take note that to determine the vertical asymptote, the graph of a rational function has a vertical asymptote at the zeros of the denominator. Meaning to say, we are going to equate the denominator by 0 to determine the vertical asymptote. And for our horizontal asymptote, okay, the graph of a rational function has at most one horizontal asymptote. Meaning to say, it can't be more than one, which varies with the degree of the numerator n and the denominator m. So there are three cases. The first case is if the degree of the numerator n is less than the degree of the denominator m, the horizontal asymptote of the rational function is at the x-axis, or its equation is y equals 0. Okay? So you must compare the degree. For the second one, if n is equal to m, meaning to say they have the same degree, the horizontal asymptote of the rational function is at y equals a sub n and over b sub m. And these a sub n and b sub m are just the leading coefficients of the numerator and the denominator respectively. Okay? So you're just going to look at, if they have the same degree, you're just going to look at the leading coefficients of the numerator and the denominator. For the third one, a third case is if n, the degree of the numerator n, is greater than the degree of the denominator m, the rational function has no horizontal asymptote. So these are the steps on how to determine, or how to graph rather, rational function. The first step is to find and plot the y-intercept if there is. Okay, because there are some instances that there is no y-intercept. Okay, how are we going to do that? We will evaluate f of 0. Okay, that will be for step number 1. Step number 2, find and plot the x-intercept. So There are also instances that there is no x-intercept. Okay, so if there is, okay, how are we going to do that? We are going to equate the numerator to 0. Okay, then solve for x. Third step, we are going to equate the denominator to 0 and solve for x. Okay, this process is also the process in how to determine the vertical asymptote. Okay, and if we're going to recall, this is the step in how to determine the vertical asymptote, as I have said on the previous slides. No, so fourth one is to find and sketch the other asymptote using dashed line. And in this fourth step, you are going to apply what you have learned on how to determine the horizontal asymptote of a rational function and how to determine if there is. And if there is a horizontal asymptote, what will be its horizontal asymptote? So all that I have presented a while ago will be applied in step number 4. For step number 5, we have to construct a table of signs to determine the sign of the function on the intervals determined by the zeros and the vertical asymptote. So we have to use a smooth curve to complete the graph between and beyond vertical asymptotes, excluding any points where f is not defined. So later, I'll show you how to graph a rational function. So for our first example, we have here sketch the graph of f of x equals x plus 3 all over 2x. And we have to state the domain and range of this function. So, first step, find and plot the y-intercept if there is. Okay, how are we going to do that? Evaluate f of 0. This is our function, f of x equals x plus 3 all over 2x. Replacing x by 0 will give us f of 0 equals 0 plus 3 all over 2 times 0. And we all know that 2 times 0 is 0. And dividing 3 by 0 will give us undefined. Since it is undefined, meaning to say there is no y-intercept. Because 3 over 0 is not a real number. For our step number 2, we have to find and plot the x-intercept if there is. Okay, how are we going to do that? We will equate the numerator to 0. Okay, as we have recalled, the numerator is x plus 3, and now we equated it to 0 and then solve for x. We have x as negative 3. Therefore, the x-intercept is at negative 3, 0. Okay? X-intercept is the value or is the point where the graph intersect the x-axis. Okay? So we have the x-intercept as or is at negative 3, 0. And if we are going to graph negative 3, 0, it is located there. Okay, as you can see, it is on the x-axis. Step number 3 is to equate the denominator to 0 and solve for x. Okay, equating the denominator to 0, 2x, that will be 2x equals 0. So, simplifying 2x equals 0 will give us x equals 0. So that will be the vertical asymptote. Vertical asymptote is the line where the graph approaches to, but it will never intersect the this line, the vertical asymptote. Meaning to say, at x equals 0, the function is not defined. Meaning to say, we have to exclude that in our domain. Okay? So we have here the domain is the set of all real numbers such that x equals 0 is not included, or x is not equal to 0. Okay? And I suppose, or I should have a dashed line or a broken line to represent the vertical asymptote, but the software that I am using do not allow me or do not permit me to do that. No, that is why it is a solid purple line. Okay, so my apologies for that, but it should be a broken line. Okay, x equals 0 or the y-axis. For our step number 4, we have to find and sketch the other asymptote using dashed line. Okay? And if we are going to compare the numerator, the degree of the numerator x plus 3, that is 1, it is equal to the degree of the denominator 2x, which is also 1. Okay? There is a horizontal asymptote. That is our first conclusion, and that is in, okay, the leading coefficient, or the numerical, or the leading coefficient rather of the numerator is 1, while for the denominator is 2. So we have here y equals 1 over 2. And y equals 1 over 2 is located there. Okay. The horizontal broken line, as you can see, that will be the horizontal asymptote. So for our step number 5, we have to construct a table of signs to determine the sign of the function on the intervals determined by the zeros and the vertical asymptote. So the number line was divided by the 0 and the vertical asymptote, which is x equals 0 for the vertical asymptote and then x equals negative 3 for the 0. So we have this interval from negative infinity to negative 3 inclusive, because negative 3, 0 is part of the solution. Since it is the x-intercept, the graph will pass through the x-intercept, so it is included. So the next interval is from negative 3 inclusive up to 0 exclusive. 0 is not included because it is the vertical asymptote. The graph approaches to 0 but will never intersect the vertical asymptote x equals 0. And the last interval is from 0 exclusive up to positive infinity. So for each interval, there is a test point. For the first, we have negative 4. Second, we have negative 1, and 1 for the last interval. Okay, these numbers are just or false between or in this interval. So for uh, for letter for the first one, we have x plus 3. Let us determine the sign if x equals negative. We have negative 4 plus 3. We have negative 4 plus 3, negative 1, and that is negative. For the second one, negative 1 plus 3, 2, that will be positive, and 1 plus 3, 4, that will also be positive. So we have negative, positive, positive. For the second one, negative 4 times 2, negative times positive, negative. Negative 1 times 2, negative times positive, negative. And 1 times 2, that will be positive. Okay, so we have negative, negative, positive. And for f of x, we will multiply negative, negative, the two negative here, above it. So we have negative times negative, positive. That's for the first interval. Positive times negative, negative for the second interval. And for the third interval, we have positive times positive, positive. So positive, negative, positive. So these will be the sign of the function in each interval. Now, it tells us that for the first interval, it is located above the x-axis because it is positive. For the second interval, the graph is located below the x-axis since it is negative. And for the last, it is also positive, so it is located above the interval, or above the x-axis rather. So we are going to use smooth curve to complete the graph between and beyond vertical asymptotes, excluding any points where f is not defined. So I have this graph, and as you can see, for the interval negative infinity to 3, I have here this. It passed through negative 3, 0 because that is the x-intercept. It is located above. And here we have, as you can see here, it approaches to the horizontal asymptote. Okay? The graph approaches to the horizontal asymptote, but it will never intersect the horizontal asymptote. So it passed through the x-intercept negative 3, 0. Now, since we obtain negative sign for this, the second interval negative 3 to 0, the graph falls below the x-axis. And as it approaches, or it approaches 0, or x equals 0, the vertical asymptote, but it will never intersect x equals 0. Okay, since it is since it is a vertical asymptote. And for the last interval, we have from 0 to positive infinity. Take note that x equals 0 is okay, x equals 0 is a vertical asymptote. That is why the graph approaches to this side of the graph approaches to x equals 0, but it will never intersect the vertical asymptote. Same goes with this one on the other side. Okay, same goes with this one. It approaches the horizontal asymptote, but it will never intersect the horizontal asymptote. So we have this. Okay, now as you can see, okay, by the way, this should be broken line. The vertical asymptote should be drawn by a broken line, but since the application that I use do not allow me to do that, so it is solid, but it should be broken. Now, the domain exclude the value of, or the horizontal asymptote and the vertical asymptote. For the domain is the set of all real numbers, okay, such that x is not 0. And for our range, okay, this is our vertical asymptote. We are not including the vertical asymptote. For the range, we have the set of all y such that y is an element of real number. It's just a real number. But we exclude 1/2. Okay, that will be all for the first part of our discussion in graphing rational function.